A rubber ring, about a quarter-inch thick, long enough to wrap around a rocket booster joint. It sits in a groove, it gets squeezed, and it holds back hot gas. That is the entire job. On the morning of January 28, 1986, ice hung off the launch tower at Kennedy Space Center. The pad had been through a freezing Florida night. Somewhere inside the right solid rocket booster, one of those rings was cold. And there is a piece of paper from the night before that nobody talks about enough. It has a signature on it. By the end of this, you will know exactly what happened in a conference call on the evening of January 27, 1986. Who said no, what they showed, how the recommendation ended up flipped by the time the call closed. And you will understand why a cold rubber ring behaves differently from a warm one, well enough to explain it to someone else at a table. Not the folklore version. The version that sits in the Rogers Commission report, in Volume 1, and in the appendix Richard Feynman wrote himself. That paperwork is where this case lives. Here is what most people carry around about Challenger, that nobody knew, that it was a freak part failure, a 1 in a million defect, the kind of thing you only find in the wreckage. Bad luck on a cold day. That reading is fair. It is what a lot of the early coverage sounded like, and it is what you would assume about any machine with millions of components. Something broke. Nobody saw it coming. Except the record does not support the second half of that. And the reason it does not is a series of memos with dates on them. Start with the joint. The solid rocket boosters were not built in one piece. They were made in segments and stacked, and each field joint between segments was sealed with 2 O-rings, primary and secondary. The primary was supposed to seat and block the combustion gas. The secondary was the backup. The Commission's report documents that O-ring erosion and blow-by had been observed on earlier flights, meaning gas had already gotten past a primary seal before, more than once, and the vehicle came home anyway. Which raises a question. If it happened before and nothing went wrong, what were they supposed to conclude? That question is the hinge of the whole file. Because a seal that leaks a little and still works is a strange thing to hold in your head. It is evidence of a problem, and evidence that the problem is survivable at the same time. The Rogers Commission report addresses this directly. It describes how the O-ring erosion came to be treated as an acceptable risk rather than a stop condition. Flight after flight came back. The seals kept being scorched. The scorching kept not mattering. That is the pattern engineers were arguing against on the night of the 27th, and the temperature made it worse. Cold weather. On the evening of January 27, 1986, Morton Thiokol, the contractor that built the solid rocket motors, held a teleconference with NASA about the launch planned for the next morning. Thiokol engineers recommended against launching. Their concern was the low temperature and how the O-rings would perform in it. That is the documented position they walked into the call with. So they had a concern. They had a forecast, and they had a recommendation. What they were about to be asked for was something harder than a concern, and it is the reason this case is still taught. They were asked to prove it. That is the part that turns a technical disagreement into a case file. The engineers were arguing from a trend. Colder joints had shown worse seal behavior, but the data set was small, the flights were few, and the correlation was not clean enough to satisfy someone who wanted a hard threshold. The Rogers Commission report examines exactly this. How the burden of proof landed on the people saying stop rather than on the people saying go, which is backwards from how flight safety is supposed to run. And within a few hours the paperwork moved. Theocall asked for time off the line. An internal caucus. Testimony given to the commission describes the caucus reviewing additional existing test data before management reached a decision. When the company came back on the line, the written recommendation had changed from do not launch to launch. Signed. Same night. Same forecast. Same rubber. What changed was who was persuaded, and of what. And the launch went ahead the next morning after that freezing night on the pad. Which brings us to the object at the center of the board, the ring itself. Richard Feynman sat on the Rogers Commission. He is the reason the O-ring question became public in the way it did. During a televised hearing, he took a piece of the rubber material, clamped it, and dropped it into a glass of ice water. Then he pulled it out and showed what it did, or rather what it did not do. It did not spring back. The demonstration is in the hearing record, simple, cheap, and repeatable at a kitchen sink, and it is the entire mechanism of this case sitting in a glass of cold water. Here is the physics. Rubber seals do not work by sitting still. They work by moving. When a booster ignites, pressure spikes and the joint flexes, and the gap the O-ring is sealing gets momentarily wider. The ring has to expand into that gap fast enough to stay ahead of the gas. That property is called resilience, and resilience is temperature dependent. Chill the rubber and it stiffens. A stiffened ring is slower to fill the opening gap. Slower means the hot gas has a window. That is not a metaphor. That is a material behaving exactly as materials do. So the mechanism is not a defect. Nothing was broken. Nothing was installed backwards. The ring was the ring it was designed to be, doing what that compound does at that temperature. The design assumed a seal that reacts in milliseconds. The Florida night lowered the temperature of the hardware. The seal reacted slower. Everything downstream of that follows from a material property, not from a fault, which is the uncomfortable part. A failure with no broken piece in it is a failure of the decision, and the decision was made on a phone call the night before. Now, why does any of this read as bad luck? Because of the flights that came back. Every previous mission where a seal got scorched and the vehicle landed safely was filed, quietly, as a success. Nobody logs a near miss as a near miss when the crew walks off. So the evidence of the problem kept arriving disguised as evidence that there was no problem. That is not stupidity. That is how humans weight outcomes. Success is loud and gets stored. The margin you burned through to get it is invisible and does not. If this kind of case file is your thing, subscribing helps. That is the whole ask. Now, the second reason it feels like luck. Nobody in the room had the counterfactual. There is no reading on a gauge that says how close you came. If the launch had been delayed and the seal never tested, the engineers who said stop would have been the ones who cost a day of schedule for nothing provable. The times the warning was right and the launch was scrubbed leave no evidence behind at all. Only the failures do. And that asymmetry is why safety cultures rot slowly rather than suddenly. Each individual decision to fly looked reasonable given the last one. The Commission's report treats this as a process problem, not a single villain. Nobody had to be careless. The reporting chain simply kept converting survived warnings into precedent, which is what makes the January 27th call so useful as a document. It is the moment the pattern got tested against a hard number, a forecast temperature, and the pattern held anyway. But there are things this file does not settle, and they matter. First, the exact wording spoken during that teleconference, accounts of who said what and in what phrasing, vary between the Commission's own hearing transcripts, later testimony, and memoirs written years afterward. Some of the most quoted lines from that night circulate in versions that do not match each other. I am not going to hand you a sentence in quotation marks and pretend the record settles it. Second, the internal reasoning inside the Theocall caucus. Testimony describes additional existing data being reviewed. How much weight it carried against the temperature concern is argued over to this day. Third, the exact O-ring temperature. Ambient air temperature at the pad that morning is documented, but the temperature of the hardware itself, inside the joint, is an estimate. Sources give a range rather than a single figure, and reasonable analyses land in different places within it. That matters, because the entire argument on the 27th was about a threshold. Nobody had a thermometer in the joint. They had a forecast, a trend from a handful of flights, and a material property that was well understood in general and poorly quantified in that specific hardware. What the Rogers Commission produced is not an accusation. It is a description of a system that let a known concern pass through it. The concern was raised. It was documented. It reached the right people on the right night, and it still did not stop anything. That is the part worth keeping. Not that someone was reckless, but that a warning can be correct, timely, and delivered to the right desk, and still lose to a request for proof it could not supply in an evening. Murphy's Law is usually quoted as a shrug. It was not written as one. It came out of engineering test work, and the useful reading is a design instruction. If a part can be assembled wrong, or a seal can be operated outside the range it was qualified for, then eventually it will be. So build the system to refuse. The Challenger file is the same sentence in a colder form. Next file, we stay with paperwork that outranked physics, a different agency, a different unit of measurement, and a spacecraft that flew straight into a planet.